Welcome to our final unit, Quasi-Single Case and Non-Experimental Designs, chapters 13 and 14. So quasi-experimental designs are designs where we don't have full control over all the potential confounding variables. One of the keys here is that we don't have random assignment. So we could potentially be using existing groups for our independent variable, and this makes ruling out alternative explanations sometimes difficult. One way that we can get around this stronger causal argument is to collect additional data so that we can rule out what your book calls rival hypotheses, or what I would call alternative explanations. We can show that this alternative explanation is not valid, does not produce significant effects or significant results. One cool quasi-experimental design is the interrupted time series design. So with an interrupted time series, what we're going to do is we're going to measure our participants repeatedly pre-test. And the idea here is we want to be able to generate a trend or a pattern in our data. Then we're going to provide some kind of intervention, and then we're going to repeatedly post-test our participants. And this sort of looks like this. So if you have the, 01, 02, 03, these are all of our pre-tests. Before the treatment, we institute the treatment, and we have multiple post-tests. Interrupted time series are really awesome when you don't really have a control group. You can think about an interrupted time series as sort of a large scale within subjects design or within participants design. But the multiple pre-tests and the multiple post-tests make this a much more powerful design in that we're able to see changes in the pattern or the trend of the data over time. This is also a more ethical version of study design. Because what it means is that we're not withholding a potentially beneficial treatment. So you can imagine if you had a reading skills intervention for, kindergarten or third graders or something like this, and you wanted to do an experiment, you would have to randomly assign schools to either get the program or not, and you're effectively withholding that beneficial program from some students during a critical time point. So interrupted time series is really useful in that we can avoid that sort of ethical conundrum. Now, some patterns of data that we might see with with an interrupted time series. So these patterns, this comes from this figure from your book, these indicate an effect. So you notice that for patterns 5 and 6, we have sort of a baseline. The pre-intervention measurements show sort of a flat trend here. Then following the intervention, the trend increases, right? The scores on whatever our outcome are, they increase, maybe reading fluency or something like this. And that stays, that trend changes following that intervention. All else being equal, we can say that relative to this pre-intervention baseline measures, because this trend has changed here, that it's likely that this trend is due to something about the intervention and not some other alternative explanation. Same thing is true here. Now, when we have patterns that look like this, though, where we have this baseline here, and then we have some treatment effect, something happens, but then we return to baseline, right? This would suggest that the treatment overall is not effective long term. There was this sort of initial bump, but then that effect went away. Here we've got just variation that doesn't seem to change. So, and again, what's useful about this interrupted time series is if we had just looked at this time point here before the intervention and this time point here after the intervention, we might conclude from these two measurements that there is an effect of the intervention. But the cool thing about the interrupted time series, because we have these multiple time points before and after, we get a sense of what this overall pattern looks like, and then this allows us to have a more sort of nuanced conclusion. If we had data that looked like this, we'd say, well, even though there's this increase, this is just part of this larger fluctuation, and it's probably not likely due to the intervention itself. Likewise, with pattern number 1 here, this is a similar thing, right? If we just looked at these 2 time points here, before and after the intervention, we might conclude that the intervention had an effect. But by being able to look at this in this larger scale, we're able to see that, well, the pattern's just been going up over time, and it hasn't really changed, right? The intervention didn't do anything that wasn't already happening here. So interrupted time series are actually pretty powerful quasi-experimental designs that allow us to actually make some pretty strong inferences about causality, especially if we, when we conduct our study, if we measure and control for lots of critical covariates, which we'll talk about. Another cool non-experimental design that's really popular, and it's gaining popularity, is the regression discontinuity design. Regression discontinuity is pretty critical for studying groups based on some kind of cutoff score. This is often referred to as sort of a rating variable or a cut point. So, for example, perhaps you have your state test data, and there's a critical score that schools, a benchmark that schools need to meet, and maybe you're doing a study where you want to design an intervention that's going to help schools that don't meet that benchmark raise their standards. So we might use that benchmark, that cutoff score, to select schools either that are not meeting the standards or that are meeting the standards. And so when we're using that cutoff score, regression discontinuity is a super cool way of designing a study. So we select based on this cutoff score, but there's a couple key pieces here. And your book has a nice table that outlines all of the different factors that you need to consider for regression discontinuity. But a couple of important ones that I note. You have to measure the rating variable before the treatment, right? So you cannot measure the rating variable after the treatment because the rating variable itself might then be affected by the treatment. So we want to avoid doing that. And the cut point needs to be determined independently. You can't sort of, look over your data and then decide, okay, well, based on what the data are, I'm going to have a cut point here, because then you're sort of artificially selecting some people to be included versus not included in your treatment and control group. So you want to make sure that we're measuring the rating variable before the treatment and the cut point is determined independently. There's some sort of state board that says this is the critical cut point for meeting standards or what have you. Now, maybe we're interested in, looking at the relationship between student scores on state tests and poverty. So one thing that we know about the relationship between poverty and standardized test scores, especially in education, is that there's a pretty negative relationship between student scores and poverty. That is to say that as poverty increases, then student test scores tend to decrease. Okay. So perhaps we have this state test, and the cutoff for the state test is here, somewhere in the middle. And we use that cutoff to divide up our sample of students into the treatment group that's going to get our reading skills intervention or whatever it is, this program that we've developed to improve their scores, right? That's the treatment group. And then the control group are the students who score above that cut point, who are already, meeting those standards, whatever that may be. Now, what's cool about the regression discontinuity is then we measure this same group of students afterwards. You can think about this, in year one, we have some state test data that shows that these schools or these students are not meeting standards. So we select them for our treatment compared to these other schools that are. And then in year two, we measure everyone again on those state tests. And we want to see if that treatment had an effect on those students who were not meeting standards prior to the treatment. And the real question that we're asking is there a significant jump? Does the regression line, which is what we'd be looking at here, does this regression line shift in such a way that that indicates that the treatment had an effect, that it raised the scores for that particular group. And this jump is what we refer to as this discontinuity. This design is super powerful for inferring causality with non-experiment, where we can't sort of randomly assign people to conditions. The gold standard for this is, of course, a randomized controlled trial, but a regression discontinuity is a really good way of providing sort of foundational evidence for a randomized controlled trial. Another useful thing about regression discontinuity is that because we're dealing with regression, we can include lots of covariates. And covariates, if you recall, these are variables that we measure that might have an influence on our dependent variable. So by measuring and including those covariates, we can sort of hone in on the effects of this treatment relative to this control group. Now, in a single case design, this is when we're using a single participant or a small number of participants to investigate a treatment effect. You can think about this as being similar to an interrupted time series. So we're going to measure our participants multiple times pre and post treatment. The two kinds that we talk about are the ABA designs and the ABAB designs. So you can think about the A as the baseline, the B is the treatment, which is silly because baseline begins with B, and so that's confusing. But A is the baseline, B is the treatment. And then the second A represents, in the ABA design, represents the withdrawal of the treatment. The second B in the ABAB is an additional treatment that we add. Okay. Now, the key here to ABAB designs is what happens when we remove the treatment. So here we've got some made-up data about the frequency of Bob being out of his seat. I chose this example because I have a son, Kalen, who is, at the time of this recording, is going to be going into first grade, and he has trouble staying in his seat in the classroom. So you might measure the baseline. So first A, our baseline. How many times throughout the day does Kalen get up out of his seat? And then we might design an intervention. So my son's teachers, recognize that Kalen gets out of his seat a lot, and so they gave him like a squishy seat pad that he can sit on and kind of bounce around on, so he can move around without getting out of his seat. So we apply this intervention to the child, and then we measure for that during that intervention the number of times the child gets out of their seat, right? And ideally, what we want to see is that there's a decrease from the baseline if we're trying to decrease a behavior, or perhaps an increase from the baseline if we're trying to increase a behavior. Then with the ABAB or with the ABA design, what we do is we remove that intervention. So you imagine my son is sitting in the classroom and he's got his little bouncy seat, and when he's got the bouncy seat, he stays in the seat more than he did without it. And then we remove that bouncy seat. And when we remove that bouncy seat, when we remove that treatment, that intervention, we measure a second baseline again, right, to see if we end up with a reversal, to see if removing this intervention brings those level of behaviors back to that baseline. And if we have an ABAB design, then we apply that intervention again, right? Ideally, what we want to see is the change to be consistent, right? So the change with the intervention decreases. When we remove it, it goes back up. And when we add it again, it goes back down, right? And this allows us to have a strong case for causality. Look, when we apply the intervention, the behavior changes in a predictable way. And when we remove that intervention, that change disappears, right? So the key to this kind of design is this reversal. Removing that intervention reverses the effect, and this allows us to infer causality. If you don't have that reversal, right? So you imagine my son, he's up and out of his seat the whole time. They institute the little squishy chair, and he's allowed to bounce around, and he decreases the number of times he gets up out of his seat during the day. And then when they remove the squishy chair, his level of getting out of his seat stays similar to the treatment condition. So we don't have reversal. When you don't have reversal, it makes it really difficult to say that, well, it's the squishy seat that was causing that change. Because we removed it and the behavior is still changed, so it might be something else that is causing that change. So with these ABA designs and these ABAB designs, you really need that reversal to make that strong case for causality. And these designs originate from behavioral psychology, B.F. Skinner and behaviorism, and so they apply better to these sort of, kinds of behavioral outcomes. Now, your book refers to non-experimental research as any research where you can't manipulate an independent variable. I have, in common parlance, referred to this as just another version of quasi-experimental design. But your book likes to make this distinction. If we're using existing groups, then it has to be non-experimental. So, there are often independent variables we're interested in that we can't manipulate, right? You can't manipulate someone being in poverty or someone having depression or someone's gender. And so there's a couple different kinds of simple instances of this kind of research that we can go over. So when you have a categorical independent variable and a quantitative dependent variable, so maybe we're looking at the differences between males and females on performance on a math test. We can look and see, is there a statistically significant difference between these groups? Now, just as a side note, a point of interest, if you have a categorical independent variable that has 2 levels and a continuous dependent variable, the statistical test, the tool that you would use for that is an independent samples t-test. If our categorical independent variable had more than 2 groups, so maybe low, medium, and high, or we were comparing blacks, whites, and Hispanics, ethnicity, then we would use an ANOVA, more than 2 levels of our categorical independent variable and a continuous outcome variable. Now, let's say we did this study, so we submitted we had a survey, we asked people their gender, we gave them some math questions to answer, and we asked the question, is there a statistical significance between the groups? And let's say we found that there was a significant difference between the groups. We might be able to conclude that there is probably a real effect or a real relationship or a real effect of gender on math performance. But we can't necessarily say that gender itself is the thing that is causing this difference because we don't have this random assignment. We also need to consider effect sizes, right? So if it's a huge difference, then we might be more convinced with a huge difference in a high-powered study versus a small difference in a low-powered study. We have to also think about this effect size and power when we're coming up with these conclusions. Another example of this is quantitative independent variable and quantitative dependent variable. So we ask you about your level of motivation, then we ask you about your performance on the math test. Lo and behold, we find there's a significant relationship between motivation and performance on the test. The students who are more motivated tend to do better on the math test. We have this statistically significant correlation. Now, just because you have a significant difference with the first case or a significant relationship doesn't necessarily mean that there's a causal relationship, right? And again, the difficulty here is without random assignment to groups or a true experimental design, we really can't determine causality directly without ruling out or considering possible alternative explanations. So we talked about this already. We're going to talk about it again. The 3 important pieces that we have to have for causality. So there needs to be a covariance, a relationship between the 2 variables. You have to have temporal antecedents, so the cause has to come before the effect. And you have to have internal validity. The relationship between the cause and the effect, or the proposed cause and the effect, can't be due to some other potential variable. And this is really the difficult piece to establish when we're talking about non-experimental research. Being able to show that this effect of gender on math performance is not due to pick an additional variable, right? Socialization or something like this. So it's pretty easy to establish this relationship. So these conditions, so covariance is pretty easy to show. Um, it is a little bit more difficult to establish temporal precedence. You can use logic to show temporal precedence. So your biological gender, biological sex does occur before you take the achievement test. But the real big issue is with this threat to eternal validity, right? You never know if the relationship you're observing is spurious, or in other words, it's due to some third variable, right? So I believe we talked about this idea. There's a significant relationship between ice cream sales and drowning. Well, that's a spurious relationship because both of those things are caused by this third variable of, summertime. So one thing that we can do to help rule out these alternative explanations is by having control. So one thing that we can do to rule out these alternative explanations is to measure and include in our study as many control variables or covariates that might have an effect on our dependent variable. So for example, there is a relationship between the number of fire trucks that respond to a fire and the damage that that fire causes, right? As the number of fire trucks goes up, the amount of damage that the fire does also goes up. Significant positive correlation. Now, clearly, the number of fire trucks doesn't cause the damage to the structure, right? The size of the fire is our third variable. It causes the damage to the structure and also causes more fire trucks to show up, right? Because you need more fire trucks when you have a bigger fire, which also causes more damage. Fire size is what we could refer to as a covariate or a control variable. So this table from your book is kind of neat. It shows this idea that when we don't control for the size of the fire, if we measure, we have data points for our small, medium, and large fire, it shows that the number of fire trucks that respond increases at a linear rate with the amount of damage that's done. And it shows this positive correlation. But when we control for the size of the fire, so we control for small fires, medium fires, large fires, and we do this statistically, mathematically control for this, then the relationship goes away, right? The relationship between number of fire trucks and responding goes away because we've removed the variability in this dependent variable of fire damage that's due to the size of the fire. Another way to sort of conceptualize this is if you imagine that your dependent variable is a circle, and that dependent variable represents 100% of the data. And when another variable, a covariate or your independent variable, can explain or affects that dependent variable in some way, those two circles overlap. So this portion here is the portion of our dependent variable that is explained by our covariate, by that other variable, that third variable. So if we remove that covariate, so statistically what we do when we include a covariate in our model is we remove the variability in our dependent variable that is explained by this covariate. And then we apply our independent variable. So it can only explain the variability that's left over, represented here by this sort of half moon shape. This is all the variability that's left over once we've removed what's being explained by the covariate. And so the independent variable in that way then is only operating on or can only affect the part of the dependent variable that's unrelated to the covariate. Now what's cool about this is if we throw our independent variable and our covariate in the model, and the covariate explains significant variability in the dependent variable, but the independent variable does not, right? Then we can draw the conclusion that, well, no, this is probably a spurious relationship, right? This covariate is really the thing that is having an effect on our dependent variable. So when we're doing non-experimental research, oftentimes we want to ask as many questions of our participants as we can. We want to gather as much data as we can on these potential covariates, on anything that might potentially influence our dependent variable. Because if we can control for all of those things and still show that our independent variable is having an effect on our dependent variable, then we can make a stronger case for that causal argument. So that's it for non-experimental, quasi-experimental, and small case designs. Short lecture. Make sure you take a look at the guidelines for assignment number 5, as well as the guidelines for the final research proposal. And as always, email me if you have any questions.